Hello and welcome back. Now we are going to perform embedded strings analysis. To start off, we'll open Flare Utilities and use the bin text. Our bin text is already on the desktop, so we can just double click on it. So we'll use the unpacked version and run it in bin text. The first string we see is the Anayze header. This program cannot be run in DOS mode, confirming that this is a PE file. Let's scroll down and see if there are any other interesting strings. We also see that this is a Microsoft Visual C++ runtime program. We see some registry strings here, so probably this is for persistence, especially this one, registry set value. And we see something interesting here. From here to here, it seems like HTML code, and we can see there's some JavaScript involved as well. And here seems like some kind of message that is going to show the user your computer is in danger. Windows Security Center has detected malware or spyware infection. It is strongly recommended to use special anti-spyware tool to prevent data loss. So it is giving a fake error message, and then here there seems to be a kind of GET request to download something from this website, download.bravesentry.com, and from the name of it, probably trying to fool the user to download a fake antivirus after scaring the user with a false message. And you can see here it's trying to download something, and this is the website. And then down here we see some kind of registry, and then here also it seems to be a string indicating some file with a .lic extension, which brings to mind probably a fake license file. LIC could be license. And here is probably the way the malware is trying to create persistence so that it can start again when the user log in or reboots the computer. And here we see the name of a file, xpupdate.exe. This could be the file dropped by the malware, and this probably is the file that this run here is going to run. So we can confirm that in the dynamic analysis later, but good to know what to look for. So we can probably make a note here on the files that we have seen. So xpupdate is the file to look out for. And the location seems to be a protected path, C Windows. Now normally malware cannot write to C Windows without elevated privileges. So when we run this malware data in the dynamic analysis, we might need to run it as administrator so that it can perform this dropping of this file in this location. Okay, so that's it for the strings analysis. Now let's see if there are any encrypted strings. To search for encrypted strings, we can use XOR search. So XOR search will search for any strings and brute force it to try to decrypt it. So XOR search this is how you run XOR search. if you run it without any parameters, it will show the help file. And then to resolve search, we can do it like this, the name of the unpack file, and then the string that you are looking for probably HTTP. So the first parameter is the name of the malware. In this case, we are using the unpacked version. Second parameter is the string you are looking for. So it will now search for this string, and then it will brute force some of the encryption keys to see if they can find a string containing HTTP. So let's press enter. And you see there are some hits, and the first line shows it has found, using the encryption key of 00, it has found this string. So encryption key of 00 means there is no encryption, so we can ignore this one. Encryption of 20 means it's just a conversion from lowercase to uppercase, so we can also ignore this one. So it doesn't seem to be any encrypted strings in this containing HTTP. We can try with this, use the search for this, because sometimes malware will pack some files, will encrypt some files containing certain PE files. And if you're looking for this, and you know that this is part of the string in the PE header saying this program cannot be run in DOS mode, so that's why we are trying to search for this string this to see whether there are any encrypted strings containing this. So press enter, and so far we only found one hit, but this one is encryption key is 00. That means this is not encrypted at all. So this is also not encrypted strings. So it seems from the XOR search, and the two most common things that we are going to search for, HTTP and this, doesn't seem to have any encrypted strings embedded inside it. So that concludes the embedded strings analysis. I'll see you in the next one to continue with the rest of the static analysis. Thank you for watching. Hello and welcome back. In this video, we are going to do PE header and hash analysis. So to start off, we will open Flare Utilities and run the PE Studio program. We will now drop the unpacked version into PE Studio and wait for it to analyze. While it's analyzing, you can see wait messages in part of some of the fields. Now that it has finished analysis, let us go and take a look at some of the indicators of compromise. And you see there are many level 1. First section is writable, and then here file references strings tag as blacklist. There are 25 blacklisted strings, and so there are also file references here. And virus total has also detected it as malware, and there are some file imports, 18 of it at level 1 blacklisted. And also the file contains writable and executable sections, 1 count of that. And it also has self-modifying executable sections, 1 count of that. And the file contains resource in a language that is tagged as blacklist, Russian language. So we'll take a look at all these now in one by one, starting with this optional header. So under optional header, you will see that the subsystem is a GUI. Therefore, it can integrate with a GUI system. And that ties in with our earlier analysis where we saw some JavaScript code to show a fake warning about your system being infected with spyware and adware. Now under the file header here, you can see the compiler stamp. This program was compiled on May 7 in the year 2007, And if you go to the resource section, under here, dialog, you can see the language is Russian. So another indication, it could be Russian in origin. And if you go to the sections here, you can see there are the text section, which is supposed to be the code section. It is writable. Now that is a red flag, because code section is supposed to be executable and readable, not writable. And it is also self-modifying. So this could be indication that the malware could be performing self-modification as it is running. And then under the libraries, you can see the IAT table. So this looks quite normal. There are a lot of exports. This is because we have unpacked it. For the packed version, if you were to analyze the packed version, you will find that a lot of the imports are not there. So very few functions imported indicates that it is a pack, but we have already unpacked it. That's why we see all this, quite a number of functions. Let's look at the imports. So let's list it according to blacklist. And here we find registry set value, indication of persistence. The malware is trying to persist itself through making a registry using this API to create a new key. And we also see it is able to connect to the internet. WSA startup is the initialization function for WinSock. And here is also the Windows networking functions being used to perform actions to get things ready for connecting to the internet. It can also execute other programs. WinExec is an API for executing other processes. Okay, so now let's take a look at so these are quite a number of indicators of compromise. And now let's do a hash analysis. So we'll first start off with the packed version, right click, and then here we hash my files. And we can copy the MD5 here and open the virus total in Chrome and see the virus totals report. Click on the search tab and then paste your MD5 hash and hit enter. And you see 60 out of 71 antivirus have detected the type of virus it is. Trojan, fake alert RS, and so on. So this confirms that this indeed is a virus. So that concludes our static analysis for this malware sample 2. Thank you for watching. I'll see you in the next one. Hello and welcome back. We are now going to start dynamic analysis using the same dynamic analysis workflow which we have used before, and we are going to do it on financial unpacked. So the first thing we do is start up the Procmon. So down here, click on the Procmon program, and then we are going to pause it, and then we are going to clear the output. Next thing, we are going to start FakeNet. So click on FakeNet down here and let it run. FakeNet will intercept all the network traffic which the malware is generating. Next, we are going to do the rec shot. So just click allow access. And now we open the rec shot tool from utilities. And then here, click on the checkbox and change the directory to C drive, the root of the file system, and click on first shot. Click on shot, and this will take a few minutes, so I will pause the video and come back when it is done. Now it has finished the first shot. You can see the message popping up here. We can click OK. And before we take the second shot, we need to run the malware itself. And we know that the malware itself needs to run as with elevated privilege, because we saw from the earlier static analysis it is trying to drop a file in this Windows location, which is a protected folder. So we need to run it as administrator so that it can do its thing. So we go back to the malware and run the unpacked version as administrator. But before we do that, we need to start the process monitor. So we click on capture on the process monitor, and then we go to the malware itself, right click, and then we run as administrator. Click yes. And immediately you see this fake message popping up: your virus is infected. Windows has detected spyware infection. It is recommended to use special anti-spyware tools to prevent data loss, and so on. And it wants you to download something. And we saw this message when we were doing the static analysis earlier. And also in the fake net, you will see that some activity going on. And over here you will see it's trying to connect to the internet and download something from the internet, from this website, download.bravesentry.com. So this is the server it is trying to connect to download additional packages. So we'll just let it run for about maybe a minute, and then keep an eye on this fake net to see if there's any additional activity going out to the network. And you can see now the process monitor is capturing the events up to 33,000 out of 87,000 now events has been captured. Later on we'll analyze the output, and we'll see whether or not it drops this file in this location as indicated by our static analysis. So far, FakeNet has not showing any additional activity on the network. Okay, I think we can stop this process monitor now. So we can stop it by clicking this icon here. And after we stop the process monitor, we are going to go back to rec shot and take our second shot. So head back to rec shot and now click on second shot and then select shot. And this should be relatively faster than the first shot. And the second shot is now complete. As you can see, the message has popped up and we can click OK on that. Now we are going to click on the compare button and select compare and output. And this will take a little bit longer than the second shot, so I'm going to pause the video and come back here when it has done the comparison. The comparison is completed and now it has popped up this text, and let's start analyzing. And from here we see that there are certain values added, and over here we see this one. A new key has been created and in this registry, and the key name is called Windows Update Loader, and the value is this path to this file. So sure enough, this is the persistence mechanism for this malware. So it is going to run this new file which it has dropped into this location, C Windows, and the file is XP update. So whenever somebody reboots the computer or logs off and re-log in, it is going to run this dropped file here. And surprisingly, there is a second persistence mechanism here. It has also created a new key called con in the same location as the first first registry location, and this time it is calling itself. So we have two persistence mechanisms. Now let's scroll down and see if there's anything else. Nothing suspicious or interesting here. And under files added, you can see that it has created two files. It has dropped two files. One is install.dat in this location, users PC app data roaming. So we can copy this out and put it in our notepad as additional notes. And then the second one is XP update, which we already did when we did the static analysis earlier and saw the same thing as well above. So these are the two new files being added. Let's scroll down. So those are the indicators of compromise which Redshot has revealed. So now let us move on to Procmon, and we are going to prepare Procmon. Click OK for export. But before that, we need to apply some filters because at the moment we have 89,000 hits. Alright, so to do the filters, we will continue in the next video. Thank you for watching. Welcome back. Now we are going to put the filters for the Procmon, and these are the filters that we are going to use, same as before. So let's get started. So the first thing we need to filter out is the name of the application of the malware. So click on the filters icon here, and then select process name, and then select the name of the malware itself, and click add, and click apply. So now it has dropped to 867 filtered. Next one, we are going to filter by the API call. So we select under here operations and select the API that you want to filter. So the first one is write file. Click on add and click on apply. The next one is set disposition information file. Click on add, click on apply, and then the next one will be rec set value. Rec set value. Click on add, click on apply. Next one will be process create. So click on search for process create. Process create. Click on add, click on apply, and next one will be TCP and UDP. So just key in TCP so that you can search for anything related to TCP. Click add, click apply, and last one is UDP. Click add, click apply, and then click on OK once it has finished applying the filter. Click on OK. And now we can see these are some indicators of compromise. He has called the write file API to create to drop a new file here, XP update, in this path, and he uses the rec set value API to create a new registry key called Windows Update Loader, and he calls the write file API to create a new file in this location, and it also set the registry value, a new registry value called version, probably to keep track of the version of this malware. And he also create another persistence key here in this location. So okay, so now we can export this. So we click on options. Before that, we have to set, make sure none of this is checked. Select columns. Make sure you check on this and this and this too. Make sure track ID is checked. Click OK, and now we save it in two formats. First format is the PML format. Select all events and the native PML format, and here change the path to the desktop where you put your malware. So for the desktop, malware number 2, and save it here. This is the PML file. Click OK, and the second version is CSV file for proc.dot to use. So file save all events, and here you select CSV, comma separated values, and the location is fine, the same location. Click OK. Okay, now we can open proc.dot and analyze it with proc.dot. So go to Flare, go to Utilities, and select, look for proc.dot and run it. Click OK, and make sure the path to dot is set. Click OK. Click the three dots here to open the CSV file in your desktop, the location where you save it. Click open, and then click on these three dots here to launch the analysis. So analysis has started. Give it some time. Now the analysis is complete, and click on the malware name itself over here, double click, and then click on refresh, and it will generate the visualization to show you its analysis. So now the visualization is done. We can zoom in. Hold down Ctrl key and scroll with your wheel, mouse wheel, and you can see. So the malware original name is Financials Unpacked, and it's created a thread, and it's created a file called XP update. And then here you can see it has also created a registry key called Windows Update Loader, and it is auto start. That means this is a persistence mechanism. And what is going to auto start? You can see an arrow coming from here, set as value. So when the user restarts the computer or relogs in, it will automatically run this XP update. And now the question remains, is this XP update the same file as unpack.exe? Is it the same file or not? How are you going to know? Right? So because here we didn't see anything called rename, just like the first malware one, we clearly saw that the malware rename itself after copying itself. But here there is no rename. So in order to find out whether an XP update is the same file as Financials Unpacked, we can use hash. Right? We can use hash. So we can go and do that now. We can create a hash for the first file and compare it with the. So we go to the location of the malware. We right click on this one, unpack, and hash my files. Now we got MD5. We copy the MD5 and put it in the notepad and call it original. Now we go to the location of the XP update, which is here, C Windows XP update, and create a hash for that as well. So we go to C drive, and we go to Windows and look for the XP update file and right click it and select hash my files. And then if you copy out the MD5 as well from here, copy MD5 and put it in your notepad for comparison. And we can see they are identical, exactly the same. So this confirms that our xupdate.exe is exactly the same file as its original name. Alright. The other thing it does is it also creates a new thread. You can see from here, create thread 2824, and this thread creates another file in this location, app data roaming, and this new file is called install.dat. And then the thread also creates another key in this registry to keep track of its version. And interestingly, it also creates another persistence mechanism here. And this time the key is called con. And this con is going to run its original file name, because obviously it did not delete the original file. So the original file is still there. So it's going to run two copies of itself. One is here and the other one is here. So we have seen quite a number of things in this analysis, indicators of compromise. So in the next lesson, I'm going to do the network analysis. Thank you for watching. I'll see you in the next one. Come back. In the previous session, we've already done the product analysis. And now in this video, we are going to do the network analysis. So the network analysis, as you know, the file is saved in the fakenet logs. And here we see fakenet has already shown that it is trying to download something from Brave Sentry. So we can probably create a snapshot of this if we wanted to. And we can use the snipping tool for that over here. And create a snapshot of fakenet output. Alright, so now we can kill fakenet since we already got a snapshot. Close here and go to the fakenet logs and look for the pcat file. So this is a pcat file. We double click and it will automatically open in Wireshark. And as you have seen before, Wireshark is used for analyzing pcat files. So Wireshark has loaded and it is now initializing itself, and it is done. So from here we can now see all the traffic that has been captured by fakenet, and we are now going to filter out the HTTP, because from fakenet we saw that it is reaching out to a HTTP server, a web server. So we filter out HTTP here. Hit enter, and now we can see here the GET request, and we can right click and select follow and select TCP stream, and there you go. And you can see here it is getting a GET request to the server to this server called download.bravesentry.com, and FakeNet has intercepted it and given its own reply by HTTP OK, and this is the FakeNet reply. And we can come down here and look at the entire conversation, which is all this, or we can click on the download list and select the incoming traffic and the outgoing traffic. So this outgoing traffic, and it shows that it is going out to bravesentry.com, and then you can go down to see the incoming traffic which FakeNet has intercepted and reply to the malware. Alright, so this is our network analysis, and this is clearly a sign of an indicator of compromise. So this is how we do network analysis. So to wrap things up, we can write a report to show all this. So this is an example of a report which you could write to list down the indicators of compromise. For example, the file system, we saw that it has created a new file called xpupdate.exe and dropped it in this location, C Windows. And we also saw that this file was set to persist to launch by creating two persistence keys in the HKCU registry. And it also created another registry setting for keeping track of the version. And it also dropped a file called install.dat. And this install.dat, if you want, you can go ahead and perform further analysis, so I'll leave that to you. And then on the network side, we also saw that it attempted to download something from bravesentry.com. So this is a sample analysis report for your malware sample 2. So that concludes our session on the practical for malware analysis 2. Thank you for watching. Hello and welcome to a new section. In this section, we are going to delve into malware sample number 3. So this video is where I introduce you to malware sample 3. Learning objectives. Analysis of the Lockybot Trojan. Malware sample 3 is the Lockybot Trojan. File identification, unpacking and decompiling using exe to auth, using Ghidra disassembler and decompiler, using XDBG debugger, using process hacker to dump memory. So as usual, be very careful when handling this Trojan. Always use a virtual machine. So go ahead and download resource from the resource section, malware sample 3, and put it in your virtual machine. I will see you in the next lesson where we will get started with the analysis. Hello and welcome back. In this video, we are going to get started with the analysis of malware sample number 3, also known as Lockybot Trojan. After you have downloaded this file from the resource section, just go and unzip it, extract to malware sample 3 folder. The password is crackinglessons.com. You will then have a folder containing the malware. It is renamed with the bin extension instead of the exe extension in order to protect you from accidental clicks. Open TreatNet and analyze it. And here you will see it says CPL exe so we cannot get much information from here. So now we'll try to analyze it with exe. Go to utilities, we will use expe-info. And it has detected it as an AutoIT program. And AutoIT is a tool for creating automation. It is not a malware itself. It is quite a popular tool, but used also by some malware authors in order to create malware. So you can go and Google for AutoIT to understand more about it. So if you search for AutoIT, you find this link here, AutoIT script. It is a freeware programming language written in VB-script. After the scripter has created a script, he or she can convert it into an exe. So this is what AutoIT is like. And malware authors will write their AutoIT script and then will convert it to an exe. So this is what we are seeing here. So exe-info-p also very helpfully suggests how you can decompile this by using the tool exe to AUT. Now if we open the Flare folder and go to utilities and run PE Studio, we can see some additional information. So we'll drag the malware into PE Studio and let it analyze the file. And you can see VirusTotal has detected 55 out of 72 antivirus has detected it as malware. Trojan offers AutoIT. Trojan spy Win32 Locky. If you go here, you see this in red, click on it, and it has detected it as an AutoIT Trojan. And the script itself is found in the resource section under RC data. So this is the location, the offset of inside the resources where the AutoIT script is found. So basically we are looking at an interpreter, an AutoIT interpreter, and within the interpreter itself there is a resource section which contains the actual script itself. So that is how it works. So we can actually unpack it using the suggested tool by exe-info-p, which is the exe to AUT tool. So we can now run the exe to AUT tool from the Flash utility folder. Look for the tool called exe to AUT. So this is compiled from AUT to exe. So now we are reversing it, exe to AUT. So originally it was in AutoIT script, but the writer converted it into an exe. So we use this to decompile. So we run this now, exe to AUT. So just read the warning here. Dropping modified or non-modified or auto-IT files into exe to AUT might result in execution, so be careful. Click OK. So now we'll take this and drop it in the decompiler, and you see a new file has been generated with a .au3 extension. This file is the script itself, which has been extracted from the malware. So you can open this, or you can read it from here, the script itself. And it is written in VBS script. So it is in plain text. But there are a lot of obfuscation, as you can see. Obfuscation is a technique of hiding the intended code so that it makes it difficult for the analyst to understand what is going on. You can also view this AU3 file by right-clicking and then opening with a Sublime Text or any text editor of your choice. Let's try to open it with Code, Visual Studio Code. In Visual Studio Code, you can view the file and scroll down. Quite a long script here, and mostly obfuscated with plenty of obfuscated strings, as you can see. All are obfuscated. If you keep scrolling down, you come to another packed file. So you can see here, the variable j is a packed file, encrypted, as you can see. So what it's doing is creating a long shellcode. We call it shellcode. So shellcode is where the code is encrypted or encoded so that you will not be able to read it, but it can run when it's loaded into memory. And here it is just appending into a big string. So it's using this append operator. If we create the first string with the variable j, and then keeps appending new string to the original variable. This is the meaning of j equals jn. So it appends all this into one huge shellcode. As you can see from the right hand column here, it's very long. Alright, so this is the second stage payload. The first stage payload was the auto-IT script, which was embedded in the resource section. We have managed to unpack that by using the exe to AUT decompiler, and we managed to decompile. So we passed the first stage, and now this is the second stage. Within the script itself, there is a second payload, which is this file here. This encrypted or encoded shellcode. So in order to make sense of all these things, we have to let this script run, and then when it's running, we have to dump the memory where this part is unpacked. So in order to know how to do that, we will need to use debuggers and also the disassembler. So in the next coming videos, I will show you how to do that using Ghidra disassembler and also XDBG debugger. So I'll see you in the next lesson. Thank you for watching. Hello and welcome back. In this video, I will introduce you to a powerful disassembler and decompiler known as Ghidra. So click on the bottom left corner on the Windows icon and then search for Ghidra. Click on the first result that you find to launch Ghidra. Ghidra is now firing up. It will show you a tip of the day. Just close it And here is your windows for creating a new project. So now we have no project. Let's create a new one. Click on File, New Project, and then select Non-Shared Project. Click on Next, and then select the desktop folder where you have unzipped your malware. So navigate to the malware sample tree and select the project directory as malware sample tree. And in the project name, you can call it malware tree. And then click on Finish. Now we have a new project, and you can see the folder has been created in Ghidra. We can now drag our malware sample here, and you can see that Ghidra has created a new folder and some other files. So we shall drag sample bin into this project. So drag it and drop it into this malware tree folder, and Ghidra will begin the import process. Ghidra will show you that it has detected the format as portable executable PE, and the language is x86 32-bit Windows. So just click on OK, and now it will load. After a while, you will get a Windows security alert. Just check both boxes and allow access. This is normal. Ghidra needs to use it. And now it has showing you the import results summary. And you can see that it has the name of the program, the processor, the size 32-bit program, and so on. Just click OK. And now it has imported it. We can see on top here there is a tool chest, and tool chests are the tools you can use to analyze the code. So over here, what we want to do is open this sample bin in a code browser. So let's drag sample bin and drop it into the code browser and begin the analysis process. Ghidra will then ask you whether you would like to analyze it now. Click on Yes. And here you can see all the available scripts or analyzers that can be used. Do not change anything, just accept the default and click on the button Analyze. And you can see the analysis process has begun, and the status will be showing on the bottom right corner of the screen. This will take a few minutes, so you need to be patient, and I will pause the video and come back once it's done. After a few minutes, it has finally finished with the analysis. Now on the left here, you can see the program trees, and this is a listing of all the sections contained within the malware itself. We have got the text, the R data, the data and resource, and so on. And this is similar to what you saw when you use the PE Studio or CFF Explorer. In the center panel is a symbol tree, and this contains all the names that are found inside the malware or the software that you are analyzing. And you can expand on them to look inside. They are grouped according to directories. You have imports. Imports contain all the DLL files and the functions within them that are being used by the program. And then exports are those which are exported by the program. And then under functions here, you can see there is one called entry. So if you click on it, in the center in the listing panel, this is called the listing window, you will see the disassembled assembly language. And then here is the entry point. The entry point is where the program first starts when it runs. And then just below it, you can see there's a call to security init cookie. This is a hint that you should look for when you are disassembling and doing the analysis of the code. And just below this call to security init cookie, you will find a jump, right? And this is the jump that will take you to the main function. Now on the right here, you will find the decompile window, and this is where you will see the C language listing of the assembly code. And this is not perfect. Sometimes it could be wrong, but it is quite close to the C language. So now, in order to find the main function, we will click on the jump that comes after the call to the security init cookie. So let's click on this to head over there. And now we are in the function that will contain the main. So on the right here, you will see that this thing also shows you the corresponding decompile code for this function. And if you look here and scroll down, you should find one function which has got 3 variables, 3 parameters, and this is the one. It has got 1, 2, and 3. This is your main function. Normally it is just below, somewhere at the bottom, below the exit function. So this is the main function that is always there for any Windows program. If you want to know more about this, you can look up MSDN. You head over to the browser and look for MSDN, and you key in the Windows. Just type MSDN Windows main function signature. And then I think this should be the one. Just click on it, and it would tell you what it looks like, the main function signature. Right. So the complete main function signature has got 3 variables: argc, char pointer argv, and child pointer environment variables. So this 3 is a standard signature for WinMain, for Windows main function. So you can use this actually to identify your main function in Ghidra. So when you're analyzing, after entering the entry, and you scroll down, look for a function which has got 3 variables, 3 parameters, 1, 2, 3, and that will be your main function. So you can right click and edit the function signature, and you can call this main. And the faster way is just to paste what you have copied from the MSDN. So 1, 2, 3, just paste it there. Or I can't paste because I copied from outside the virtual machine. So over here I can change the signature. The return type will be int. The first parameter will be the count, how many variables you have in your Windows. Okay, the first one is in argc, second is child v, and third is child environment. So this is what we are going to change to. So the first parameter, you don't have to do this, but I'm just showing you so that you know how to edit the signature of any functions. So this one should be argc, argument count. The second will be your char pointer argv square bracket. But inside Ghidra, you cannot use a square bracket. Ghidra doesn't understand it. So you have to convert the square bracket into 2 stars in front. And finally, the last parameter is your environment variable. Just put env, and this one will be a char pointer as well. So this is how you can edit the function, the signature of any function. Just click OK. Once you click OK, the name of the thing will be reflected here automatically and inside here as well. So you can click on this to view it here. Alright, this is the one, main. You can see that? Call. So these are the parameters pushed to the stack. We have 3 push before call. Alright, so here is the same. 3, 1, 2, 3. Then you have a call. So these 3 pushes, 1, 2, this one, 1, 2, 3. Then a call. So this call main function makes use of these 3, 1, 2, 3. So this is your main function, right? So now you're located main. Remember, you always have 3 push before call. Or another way is you can look for a function which has got 3 parameters, and that is your main function. So now you can click on this and go straight to the main function, and this is your main function. And here also your decompile window will change to show you your main function. Right, so this is your main function, and you can scroll down and take a look at it, and this is what it looks like. At this stage, you can see that this is the main function, and there are many other smaller functions within it. So normally we will investigate each one of it in turn by double clicking and entering it. So if you double click and enter something, and then you want to step out of it, you just have to click the back button here. See, now you have stepped into it. You want to go back, just click back, and then you step out of this function to go back to the parent function. Now you're back in main, right? And then you can also click on Windows here and click on function call graph to look at the graphical representation of all these functions. So Ghidra will show you the function call graph. So from main, you have all the other functions within main itself. This is one way to view it, and you can zoom in and out by using your mouse to scroll. And then from main, you can see all the sub-functions within it. And then each one of these, you can again click on it to enter it, and click on it like this. And then there's a plus there at the bottom. If you click the plus, you expand and show you what is inside this function itself. And you expand to show you what is inside this function. And you can see at the bottom here all the functions within it. You can move. You can just drag and hold with your left mouse, and it will move like this. And then if you click the minus here, you can see a minus there, you will collapse it again. Alright, now another tool you can use is this one, Windows, and then go down to function graph. Click on function graph, and you will look at, it will show you the graphical form in square blocks like this. And then here you can zoom in and out using your scroll wheel. You can zoom in, you can move by dragging and moving around. You can also move your blocks around by dragging the title bar of each block and moving it around so that it can align itself to make it easier to view like this. And then here you can see the if else blocks are clearly marked here like that. And then at the bottom is an overview of your graphical view, function graph view, like this. Okay. Now then, this is a graphical view of your decompiler here. For example, function 3BEA is over here. So basically you now enter each one of these calls here to see if there are anything interesting. Okay, so as you enter each one, you will find that there is one particular function which is interesting, and just click on it to go there. And here you can see there is one function API called isDebugger present. So it appears that this malware is checking whether there is a debugger attached to the program. So it returns the result in bvar1. So if you want to know what isDebugger present does, you can Google for it in MSDN using the method I taught you earlier. So if the isDebugger is present, it will return true. So true will be 1. If debugger is not present, it will return 0. And here is a test. It is testing whether the result is 1 or not. If the result is not equal to 0, that means debugger is present. And so it will pop up a message box to let the user know that this is a third-party compiled AutoEat script. And then it will go somewhere else. But if a debugger is not present, then this will be false. And then it will go down here and do what it's supposed to do as a malware. Alright, so we have to somehow change this to be false. We don't want the malware to detect the debugger. So in order to do that, we need to use another tool called XDBG. XDBG is a powerful modern debugger where you can modify the running program to change the value of any kind of API which is running. So to do that, I will show you in the next lesson. Thank you for watching. I'll see you then. Welcome back to another lesson. If you remember, earlier on we did extract the script using exe to AUT and saw that there was some embedded code inside the AUT script itself. So now in this lesson, I'm going to show you how to let the program run into memory and then let this script expand and unpack itself into memory. And then we are going to dump using another program. So in order to let this thing run and expand and unpack itself into memory, we need to use a debugger. So the debugger that we'll be using is XDBG down here. So there are two, 64 and 32. So since this program is 32-bit, we run x32dbg. So once x32dbg has started, we need to do some settings first. Click on the options, preferences, and here uncheck system breakpoints and TLS callbacks. We want it to straight away go to the entry breakpoint. So click save. And then here we can open the malware itself. So now we are doing dynamic analysis. So go to the desktop, which contains the folder for your malware. Select all files and open the sample bin and click open. So now we are going to run it. So we just click here on run. But before we run, notice that this is already at the entry point. Now from our analysis using Ghidra, we know that there is a isDebugger present being called. So we have to put a breakpoint for this isDebugger present. Alright, so from here we saw that the virtual address of this isDebugger present is at this 403b7a and the base address is 004. But if you look at our XDBG, the base address might not be the same. So let's click on memory map, and we notice that our base address is different. It is 12 instead of 004. This happened because of something called ASLR. ASLR is a security measure in order to randomize the base address when the program is running. So in order to convert this into the correct address where each debugger present is loaded in memory, we have to do some calculation. So from here, we know that the offset is 3B7A. So all we need to do is take 3B7A, and then from here, add the 3B7A to the base address of 121000. So that will give us 1213B7A. 1213B7A. So all we need to do is go to that address. So right click and then go to expression, and then here you put 1213B7A, and then click OK. And that will take us straight to the is debugger present, as you can see. So we want to put a breakpoint here, so we right click on this and then set breakpoint toggle, and the breakpoint is set. So now when we run, it will stop at the breakpoint, and now we see the value of AX is this. So let's run step over this. So we click on this to step over it. When we step over it, the result of this API call is stored in the register EX. So now we see is 1, which means that debugger is detected. So we want to modify this to 0. So just right click on this, modify value, set it to 0, and click OK. So 0 means that is debugger present is false. That means it did not detect a debugger. The next instruction is going to test whether or not this EX is 0. So since we have changed it to 0, it is not going to jump, it's going to go straight. J and E means jump not equal. So if EX is not equal to 0, then it's going to jump. But because we have already modified the register to make it 0, so it is not going to jump. So we can test it out by stepping. And then when you click on this, you see it is not going to jump. This arrow here is grayed out. Alright, so we have just defeated the is debugger present check. So now the next thing is we want to go to the location where it's going to unpack the code that we saw in auto IT script. So to do that, we should put a breakpoint on virtual alloc. So we can put a breakpoint by going to the command line, type vp virtual alloc, and then hit enter, and it says breakpoint set. If you go to breakpoint tab, you can see all the breakpoint that is set. So that we have set virtual alloc now. So let's run to virtual alloc. Okay, just let it hit the virtual alloc. Give it some time. Virtual alloc is now hit. It has hit the breakpoint. So virtual alloc is always used by malware just before it unpacks itself. Its function is to allocate memory so that it can unpack whatever it's supposed to unpack. So now we're going to step over, let it execute the virtual alloc. Now it's going to execute it by jumping there. And now it's going to execute. Alright, so this is where virtual alloc is going to execute. So let it step over until it hits the call. It is pushing all the parameters to the stack in preparation for the call. Great. So now step over, and the return address is here. So this is the address where it has allocated memory. If you need to learn more about virtual alloc and the return value, you can MSDN for virtual alloc. Google for MSDN virtual alloc. Right, but now we just want to get to the address where it has allocated memory. So right click on EX and follow in dump. And this is the allocated memory for the malware. Malware has allocated this memory in this location by calling virtualalloc. So now we run again, and you will find that it will call virtualalloc a second time. But before we run it again, we want to see what are the permission settings for this 3C, 6C followed by 40. So we can go to memory map and look for that location. We can right click this and then here follow in memory map, and we see this location, the permission has been set as ERW, executable, readable and writable. Okay, so now we can run it second time so that it will trigger the virtualalloc one more time, and then we step over again, and now it's going to push new parameters to the stack in readiness to call virtualalloc a second time. So just step over. Alright, now it's about to call this and watch the return address. Alright, so it has allocated some more space in this location. Right, so the earlier location was here, this location at 6C40. So we make a note. We can open Notepad and make a note of the first memory address where the malware has allocated space in memory to do something. So the first memory address is 006C followed by 40. Now we are going to see what's the next address is going to allocate. 00C0. So the second location is 00C followed by 50. So there are two locations in memory. Alright, so now we can right click on this and then follow in dump. And see, this is another location in memory where the malware has allocated space to unpack something. And if you go to the memory map, you can see the permissions. So you right click on this and follow in memory map, and we can see at this location in memory, it has also set it to be ERW, meaning executable, readable and writable. Okay, so with that we now know where it is going to unpack itself another code inside memory. So next lesson I'm going to show you how to extract that code from the memory itself. So before we do that, we're going to put a breakpoint here, right click, and then we are going to set the hardware breakpoint, hardware execute over here. So whenever the malware has unpacked and when it is about to execute, we want it to break over there. So that's why we are putting a hardware breakpoint. Hardware execute. So now if you go back to breakpoints, you will see we have set a hardware breakpoint at this location so that we can break whenever the malware is about to execute the code inside here. So I will do that in the next lesson. I will show you another tool where we can dump the memory just before it executes this. So I'll see you in the next lesson. Thank you for watching. Hello and welcome back. In the previous lesson, we have put a hardware breakpoint at the location where the malware is about to unpack its secondary payload, and we know that after unpacking it's going to execute because it has set this permission to be executable. So now we are going to run and let it hit our hardware breakpoint. And it has hit our hardware breakpoint. See that? And it has populated this region of memory with the unpack code from auto IT. So now it's going to execute, but we're not going to let it execute. We are going to use another tool to browse this region in memory and dump the content. So we can use a tool called Process Hacker to do that. So let's go back to our Flare here, open the Utilities folder and look for Process Hacker. So we have Process Hacker here, just fire it up. And then over here, we are going to look for our malware, which is in memory. And scroll down and you should see sample bin. This is the one, right? So just double click on sample bin and then go to the memory tab and then expand the window. And now we are going to look for the address that we have set the hardware breakpoint 00C. So just scroll down and look for 00C. And then here we see C followed by 5 zeros. This is the address that we set the hardware breakpoint. And the permission is read, write, execute. And if we double click on this, we can see that this is the code that has been unpacked into memory. And you can compare it and see it's the same. See this here and here is the same. Right? Alright, so now we can dump this by clicking the Save button here. So we are inside Process Hacker and we are now going to dump this memory in a separate file. So just click Save and then we can save it in the desktop in the same folder as the malware and give it a different name. So we are going to call this unpack sample and then we're going to say save like that. So that's how we unpack the code, and this unpack session here is actually all this thing. So the malware, we managed to unpack it by letting it run and dumping it from Process Hacker. So that's how we do it, and once you've already unpacked this, you can go ahead and analyze the new dump file, unpack sample with Ghidra, and go ahead and do whatever analysis you need. So this is quite an advanced topic, but I won't go into that because this thing is quite complicated. So it's just enough for me to show you how we can use the disassembler Ghidra to look for the correct place to analyze, and how we can then use what we found in Ghidra inside a debugger to put the correct breakpoints, and then from the breakpoints that we have set and let it unpack, we can use Process Hacker to dump the unpacked section of the code from memory into a file for further analysis. So with that, I will end this section here, and thank you for watching. Hello and welcome to a new section. In this new section, we are going to reverse engineer new malware sample 4, which is also known as the Tesla Crypt ransomware. The learning objectives for this section are analysis of the Tesla Crypt ransomware, file identification. For this, you will need to use the usual tools for identifying the file type, like TreatNet for example. And then we'll be doing something different. You'll be trying to find out what the packer is, but you won't be able to find any signature. This is because Tesla Crypt was packed with a custom packer. But anyway, you need to go through the process of trying to identify it using Detected Easy, also known as DIE, and also EXEPE info. But both of those tools will yield no result. It will not show any packing. But that does not mean it is not packed. So to find out, dig further into whether or not it is packed, you need to use PE Studio, and PE Studio will show you that the number of imported functions are very few. And another thing is, in the sections, you will find that the entropy is very high, above 7. Entropy maximum is 8. Normal unpacked code entropy is only 5 to 6, but anything above 7, usually it means it is packed. So you need to use your PE Studio and analyze the sections to look at the entropy. Then you will use XDBG debugger to let the program unpack itself into memory, but you need to put the breakpoint on the correct API. And the technique to do that is to use a breakpoint on the API known as virtual alloc. And then you need to let it unpack itself, but before it runs the unpacked memory, you are going to use another tool to dump the memory for the unpacked addresses, and that will be Process Hacker. And then lastly, you will start the Ghidra program to disassemble the dumped memory, and then you can analyze it if you want. So this is the learning objectives for this session. If you feel up to it, I encourage you to give it a try on your own before you take a look at the next videos on how I do it. So go ahead and give it a try. Good luck, and see you in the next one. Thank you for watching. Hello and welcome back. In this session, we are going to do file analysis as well as packer detection. So in the previous section, I already provided this file for you to download from the resource section. So just unzip it. The password is crackinglessons.com. And then open the folder, and this is a real life ransomware, Tesla Crypt ransomware. So now we are going to analyze it with TreatNet to see the file type. And the file type is exe or DLL, so it's a Windows executable. Next, we will then try to detect if there are any packers. So we go to Flare Utilities and we open DIE, Detected Easy. We then use Detected Easy to open our malware. And it did not detect any packers, but that doesn't mean there are no packers. The other thing is entropy. You can click there and it tells you that it is packed 95%. So it is 7.6 entropy. Entropy is a measurement of how uniformly the bits are distributed across the file. So if the entropy is uniform and random, really randomly distributed, it is not natural. It means that it is encrypted or encoded file. Normal files will not be so random as to the distribution of the bits. So that is the meaning of entropy. The maximum entropy is 8.0. Anything above 7 is usually packed. Normal unpacked files will have the entropy of around 5 to 6 or maybe slightly higher than that. So as you can see, even though the packer is not detected, yet the entropy is very high, 7.6%. Then next thing we do is we can use exe info pe to analyze this file. And it says that unknown exe, and it also failed to detect if there is any packer. So our first hint that it is packed came from Detect Easy's entropy, high entropy. Alright, next thing we do is analyze this file with PE Studio. So in PE Studio, let's open it now with PE Studio, and we let it analyze the file first, and click on the main file here, and then here you will see the signature is not available. It doesn't know what file it is or whether it is packed. And then you can see the description is Nana app. File type is executable. So let's wait for it to complete the analysis. As you can see, waiting here. Now the analysis has completed, and we can go and see the libraries. There are 4 libraries, but very few imports, which is unnatural. We go to the APIs, the import address table, and you can see here only 1, 2, 3, 4, 5, 6 APIs. A normal program will have more than this, much more than this, maybe 60, 80, 100 APIs, but this one has only got 6 APIs that came from these libraries. So this is a definite indication that it is packed. Next, you can go and look at the sections, and over here you can see very suspicious looking sections: para, CRT, erloc. And then you look at the sections here. Erloc, the entropy is very high, 7.6. CRT entropy is also very high, 7.883. So another indication suggesting that it is packed. Take a look at the strings. And over here you can see some of the APIs mentioned in the string. Let's scroll down and see what else we have. Okay, not much. You can see most of the strings are like junk characters. Another indication that it is probably packed. So from here you can more or less conclude that there are very high probability that this malware is packed. So with that, we'll stop this session video here, and we can now know what to do. The next step will be for us to try to unpack this malware. Since it is a custom packer, we cannot use any of the available ready-made unpacker that are available from the internet. So we have to unpack it manually. So for that, I'll see you in the next video. Thank you for watching. Hello and welcome back. In this video, we are going to use XDBG to debug the program, the malware, and we are going to analyze to look for the evidence of unpacking, and then after that we will use process hacker to try to dump the memory. So let's begin. Since we saw in PE Studio that it is a 32-bit program, we use a 32-bit version of XDBG. We then set the options, preferences, uncheck system breakpoint, and uncheck TS callbacks. Just leave the entry breakpoint. Click Save. We then open the malware. Select all files. And you will see that it has hit the entry point. We will now put a breakpoint on virtual alloc, BP virtual alloc. Press enter and confirm that the breakpoint has been set. Double check here under the breakpoint tab, virtual alloc. Now we will run and let it hit our breakpoint. So we will continue this step. It will jump to virtual alloc, and now it is going to push the parameters to the stack in preparation to execute virtual alloc. Now it is going to call the virtual alloc and return the allocation of memory in the EAX register. Step over, and this is the memory that has been allocated. So we right click on this and follow in dump. And you can see here it is currently blank, and we want to see what are the permissions, so we can right click and follow in memory map. So currently it is readable and writable. Next we will run again to see if we hit the virtual alloc the second time, and it has hit the virtual alloc a second time. Now we will step over again as before. It will jump again to virtual alloc, and now it's going to push the parameters to the stack, and it is going to call virtual alloc a second time. So we will keep an eye on EX. Step over, and this is the second allocation of memory. So now we'll right click this and follow in dump number 2. And we come down here, we see dump number 2. This is the second location in memory which has been allocated for unpacking. If we go back to the earlier memory that was allocated, you see that the malware has unpacked something there. Now the second one is over here. So let us run and see what happens to this, but before that, let us go to the memory map and see what are the permissions that has been set. So you right click on this in memory, follow in memory map, and this time at this new allocation, it is set to E, R, and W, meaning executable, readable, and writable. So now let us run and see what happens down here. As you can see, it has unpacked itself into memory, MZ. You can take a look here. This is the magic byte for a P header, and double confirmation, we can see the string, this program cannot be run in DOS mode. So this is confirmation that it has unpacked the executable and other executable inside this memory location. So now we can try to dump this memory. So for that, we will use process hacker. So we now open Flare, Utilities, open Process Hacker. And scroll down to look for the ransomware over here. Double click on it and take a look at its memory. Let's expand this. Now we want to go to this memory location, 36 followed by 4 zeros. So if we scroll down, we can see over here, read write executable. So if we double click on this, we can confirm that indeed there is a P header over there. And we can compare it with what we saw in our x64 DBG, the P header at this address. So now we can dump this. So click on save, and we can dump it in our folder. Over here we can call it ransomware dump. Click save. So we have now successfully unpacked the executable that was found in memory. So in the next video, I will show you how to open the file for analysis using Ghidra. Thank you for watching. Welcome back. In this video, we are going to analyze the dump file with PStudio and Ghidra. So let's start off with PStudio. Open up PStudio and drag the dump file into it to let PStudio analyze the dumped file. And PStudio is now analyzing. And looks like we got the wrong dump file. So we need to repeat the process of dumping. This is not the right P file, since there is no libraries and no imports. And even if you look at strings, there is nothing much there. Okay, so we have to repeat it. So I'm going to try again. Open it with XDBG. Sometimes it's a matter of trial and error, so it's quite okay. So we'll open the malware again. And then we'll put our breakpoint on virtual and run to the first breakpoint, step over, okay, so now this is the first one. We can follow in dump. Alright, now we're getting a different address, 22 followed by 4 zeros, so we can put a note there. Zero zero 22 followed by 4 zeros, 1 2 3 4. Right click, follow in memory map, is readable and writable. Now we run again, and it has populated that first memory with some unpacked code, and it has hit our virtual alloc second time. So let's step over. Okay, let's run the virtual alloc now, and it has allocated some more memory here. Right click, follow in dump number 2. This is the one. Right now we're going to examine it in memory map. Right click and follow in memory map, and you see this one is executable, ERW. Okay, so we are going to copy this address. Right click, copy value, and put it here. We have 2 addresses. Okay, now we run, and you see it has populated this second one with this unpacked code. So now we'll open in Process Hacker. We open Process Hacker to try to dump, but this time we're going to dump a different location. Process Hacker. Go to our ransomware, go to memory, and according to our notes that we have written down, it started dumping at 22 followed by 40, which is here. Earlier on we dumped something else, so now we're going to dump everything starting from here. Right click, and we are going to save, and we are going to overwrite the earlier one, replace it. So now we are going to open it with PE Studio. So we go to our utilities folder and fire up PE Studio, and now we analyze the dump file with PE Studio and see if we get any libraries. Alright, probably no, because it doesn't have a PE header at that location. So we'll close this now, and then we analyze it with a hex tool, hex editor. I'll be using 010. Right click, open with 010 editor. Okay, you see there is no PE header there at that location. So we can search for PE header. The magic byte is The magic byte is 4D5A, so we search for 4D5A. 4D5A. 4D5A is the hex for MZ. And we found a hit here. There is one hit here. So this is the location where I have a P header. There's another one here. Another MZ here, header here. So it seems there are quite a few. Alright, so it will take a lot of time to go through all of them to see which is the correct one. So to save some time, I will cut short this, tell you that the second one is the correct one. But if you are going to try this, you need to go through every one on the P header and then open it in P Studio. So in order to open a P header in P Studio, we have to delete all the one which is the wrong one. So we select the wrong bytes and delete it. Hit delete. So now we're going to save this. And then now, once it's saved, we can open this P Studio to reanalyze it. So we go to Utilities and open P Studio. So it's actually trial and error, sometimes takes a lot of work. Even a dump file does not necessarily contain the correct unpacked code. So it's a matter of trial and error. If you find a few MZ headers, you need to try each one of them like how I'm doing here until you get the right one. So the right one is now the second one, and we are trying to analyze it now. So the new dump file is here. Let's see if we can get a P header this time. Okay, we have a P header. See if we can get any libraries. If we can get libraries and imports, that means we are correct. We have already extracted the correct unpacked code. So give it some time to finish its analysis. And it has finished analysis, and this time I think we are correct. You can see there are so many libraries and so many API imports. That means we have correctly unpacked the file. You see that? So many. And then if we go to strings, let's see what strings we get. Alright, we can see there is some kind of 64 and 64 hex 64 encoding. Okay, let's scroll down and look for anything else. It's still being obfuscated with hex 64 encoding. And there is some registry key here. So this is correct, much more information than the previous one. So this is a kind of persistence here. Let's scroll down and see what else we have. And we have a HTTP here, a URL. So that could be the server that is trying to connect to. So this is a good sign or indicator of compromise. And here could be some kind of message to show the user. Maybe it's a ransom note. Yes, it looks like it. So let's expand this further. There you go. So many URLs. You can see some ransom, probably the ransom note and some URLs here. Okay, so this is a positive sign of indicator of compromise. So looks like we have done the correct unpacked code. So in the next video, we will start to We'll show you how to open it in Ghidra if you wanted to use Ghidra to analyze this. So thank you for watching. I'll see you in the next one. Hello and welcome back. In this video, we are going to analyze our dumped unpacked file using Ghidra. So let's start up Ghidra, search for Ghidra, and fire it up. Let's close this. We'll create a new project, file new project, non-shared, click next, and navigate to the project directory on the desktop. Okay, we will use this one, and we give a name malware sample 4. We will then drag the dumped malware into the folder to import it. Ghidra has correctly identified as a PE executable x86 32-bit. Click OK. Okay, it has imported the file now. Click OK. Click Allow Access here. This is the Ghidra needing the access. And now we're going to start the analysis. So we just drag the file into the code browser to start the analysis. It asks us to whether we want to analyze. Say yes. And then here's a list of analyzers. So make sure the compiler parameter ID is checked. Scroll down and check on this window PE propagate. And then for the PDB, no need for this. Click analyze. And then keep an eye on the bottom right hand corner for the progress. This will take a few minutes, so I'll pause the video and come back when it's done. Finally, after a few minutes, Ghidra has completed the analysis. So let's take a look at the entry point under functions. So if you want a faster way, you can go to exports and look for the entry function. So double click on this and you go straight to the entry point. And then now you see here the entry point. It has got the security init cookie, which is commonly found in Windows PE programs, followed by a jump. So if we look at the entry function here, scroll down, and down here you will see command wincmdl, which seems like a environment variable function, and shortly after that you get the function at this offset 41EFC0. Then shortly after that you have an exit. So this could be the signature for the winmain. And we know that this is a GUI program from earlier analysis, so it has got a specific signature. We can open up the MSDN and take a look at winmain signature. So let's open the browser and head over to MSDN for winmain signature. Type MSDN winmain and take a look at this second result, and this is the winmain signature. So we can copy this copy, do not copy the semicolon, and then come back to Ghidra, and then this one we can double click to enter the function. So now we can edit the signature. So let's do that now. Right click, edit function signature, this one. So we paste it here and then remove the WinAPI prefix here, and then click OK. Now under this we have to specify the string, pw string, pointer to Windows string, and it will update his signature accordingly, as you can see. So this is the WinMain. So every GUI program in Windows will have a WinMain, and you can see, so this is the WinMain function where all Windows will start executing. And here's a lot of interesting functions: delete file, version. So you can spend a lot of time in analyzing this unpacked code. See, let's create thread here. So this function, this malware is creating additional threads, and so on. Okay, so I'll leave the analysis to you. So the objective for this session was to show you how to detect custom packers, and then how to find the correct memory to dump. You also now know how to open up and identify the WinMain. So with that, we have come to the end of this section, and I'll leave this to you to do your own analysis with Ghidra. So thank you for watching. Hello and welcome back. This is our 5th malware sample, which is Simda Trojan. The learning objectives: analysis of Simda Trojan, file identification, identifying custom packer with PE Studio, identifying abnormal function epilogue, using Ghidra and XDBG to analyze abnormal epilogues, unpacking and dumping embedded code, and this will be an alternative to the virtual alloc method which we have studied in the previous sections. A normal function will have a following prologue and the following epilogue. It will have a push EBP in the prologue, followed by a move EBP ESP. This will be followed by multiple lines in the function body and ends with a function epilogue, which looks like this: a pop EBP followed by a ret. So every function will be having this function prologue and function epilogue. So this is what we call a normal function. In malware, we can find sometimes abnormal function epilogues. Unpacking code is often a one-way. We will look for code with abnormal transfer control. This code would lack a standard epilogue. There will be a jump instead of ret, sometimes a push ret, and other deviations. And these often happen at the end of a function, so we shouldn't get caught up in all the details in the body of the function. Fake returns. This is an example of an abnormal function epilogue. Sometimes we will see a push which pushes an address to the stack Following that, there will be a read instruction. Normally, we won't find a push just before a read. We were supposed to have a pop before a read. However, in this abnormal malware code, sometimes you will see a push before a read, and the read will return the whatever address is on the stack. So this read has no intention of returning to the caller of this function. Instead, the read is a mechanism to jump straight to the address in the stack, what is on top of the stack. And what is on top of the stack is the embedded code itself, which contains malicious instructions. So all this is one way. One way because the read has no intention of going back to the caller of this function. That is why we say it is one way. Unexpected jumps. Sometimes we will have some pushes and then followed by a jump straight to the read. Why? Because the read will have contained the address of the embedded malicious instructions or malicious code. So the jump will come unexpectedly straight to the read. So the read will now jump straight to the embedded code referred to by the address on the top of the stack. So this is called unexpected jumps. Sometimes malware will use shellcodes to try to make it difficult for the analysts. Now, what are shellcodes? Historically, shellcodes are machine code that spawns a command shell, for example, a CMD or a bash shell. And shellcodes are typically injected into vulnerable programs, for example, in the buffer overflow exploit, where the return address is overwritten to point to a new address containing the shellcode. If shellcodes are used in the above way, they are known as exploits because they are typically exploiting the vulnerable program. In malware, however, shellcodes can do anything, not necessarily spawning a command shell. For example, it can unpack malicious instructions or insert fake returns or unexpected jumps. And you can refer here for more information about how to write shellcodes and what are shellcodes. This is an example of a complex malware which contains unpacking techniques. For example, the malware in the epilogue itself might push an address to the stack, and that will be followed by return. So the return will then jump to the address on the stack and go to the shellcode in memory. And the shellcode in memory will contain an abnormal epilogue itself, whereby you will find a push address to the stack followed by an abnormal return. And this return will return to the address on the stack of the shellcode. And that address will be an address containing the embedded malicious code. So this is like a two-layer unpacking mechanism. So in the next lesson, we are going to start to analyze malware known as the SIMDA Trojan, which makes use of this two-layer unpacking mechanism. Thank you for watching. I'll see you in the next one. Welcome back. In this lesson, we are going to do file identification of the malware sample 5, and we are going to try to identify whether or not this Trojan is written with a custom packer So let's get started. You should have downloaded this from the previous lesson, from the resource section. Unzip it, and the password to unzip it is crackinglessons.com. After unzipping it, we will now analyze it with TreatNet to see what type of file it is. We drag the malware sample into TreatNet, and TreatNet reports it is an exe PE executable. Next, we will analyze it with DIE. DIE stands for Detect It Easy. Click on the 3 dotted lines and navigate to the folder on the desktop containing the malware sample and open it. Detect It Easy has failed to detect any packer. Let's click on Entropy. Entropy reports that it is not packed. Next, we will analyze it with exe info PE. Drag the malware sample number 5 into exe info PE. exe info PE also says that it is not packed. So, the next thing to do to confirm whether it is really packed or not is to use PE Studio. So let's open up PE Studio. Let us drag the malware into PE Studio and allow it to start analyzing. Give it some time. PE Studio has finished analysis, and clicking on the main link here, you will see there is no known signature. And the file type is executable, and it has a MZ header, so it is a PE executable. And if we click on libraries, we see there are 3 libraries and very few imports. If we click on the IAT, we see there are very few API functions that are imported. 1, 2, 3, 4, 5, 6, 7, only 8. So this is positive confirmation that this malware is packed. We can also click on the sections here, and we can find abnormal sections like .t2212, 2211, and so on. Even though the entropy here shows is quite low, that does not mean it is not packed. If we click on the strings here, and we will scroll down, and you will see that most of it are unreadable. Again, a good indicator that this malware is indeed packed. So now that we have concluded that this malware is indeed packed, we can start to investigate in what way is it packed and how to unpack it. So we'll do that in the next lesson. Thank you for watching. Hello and welcome back. In this lesson, we are going to use Ghidra to try to investigate how this thing is being packed and then get some idea on how to unpack it. So go ahead and launch your Ghidra. Let us create a new project. Non-shared. Click on Next. Click on the three dots to navigate to the desktop. Select the folder containing the malware and give it a name. Call it Simda. Click on Finish. Next, drag the Simda malware into the Simda folder. It has identified it as a PE executable. Click on OK. Check on both and click Allow Access. And then click on OK. Next, drag the Simda malware into the code browser. It says that it has not been analyzed and asks you if you would like to analyze it. Click on Yes. Make sure you check on the compiler parameter ID. Scroll down, uncheck PDB. Scroll down and check on Windows PE propagate external parameters and click Analyze. And then keep an eye on the bottom right corner for the status and progress of the analysis. It might take a few minutes, so I will just pause the video and come back when it's done. Just click OK to dismiss this, and now it is completed. Now, if you take a look at the imports, you will find very few functions which confirm our findings earlier, that because so few functions, this is probably packed. Now, let's go to the entry point. Before that, we are going to edit our preferences, tool options. For our listing fields, we want to cursor text highlight, left mouse, click apply. So this is the entry point. And then if you scroll down to the return here of this function, you will notice some abnormal returns. A push just before a ret, another one here, push just before a ret, and so on. So this is what we mean by fake returns. So what it does is it pushes this onto the stack, and then it returns to this address. So now you will jump over here and execute this. And this thing again push this to the stack, and then when it returns to what is on the top of the stack, which is actually this. And again here, it pushes this to the stack, and then when it returns to this as well, which is actually over here. Now because of this non-standard ways of the epilogue, this thing has not been disassembled by Ghidra. So this is not a complete function. So in order to try to reconstruct the function to make it complete, we can tell Ghidra to disassemble this part which has been left up. So we just have to right click this and then click disassemble, and Ghidra will assemble all this for us. The next thing we want to do is to no-op all this up and then rebuild the whole function again to incorporate the newly disassembled region. So to do that, we can select all these and right click and then clear code bytes. So now we can go to the hex editor and no-op all this out. So we select the windows here and select bytes, which will open up the hex editor. And then now, in order to no-op all these bytes here, 689A and so on, which is referring to all this, we will click on this icon to enable the editing. And then we can come back down here and no op it. And as you no op it, the no op hex is 90. 90 means no operation. That means we don't want anything to be executed at these addresses. So we just keep on typing 90 repeatedly, and as you type 90, each one of these will reflect the change. So we are going to insert all these 90s, also known as no ops or no operations, all the way up to the last byte C3 here. So let's continue to do that. And the last one. So now that we have no op all this, we can lock it again, and then now we can repair this part of the code to tell Ghidra to rebuild the function to include the bottom section which has just been disassembled. So to do that, we just select somewhere here on top here, and then right click and select clear flow and repair, and then the default is repair flow. Just click on OK. Okay, so now Ghidra has rebuilt the thing, as you can see, to include this new section of the instructions, and we will then create a new function to reflect the change. So you can see here there's a new function here which now shows you the exact original function. So now we can click on the last one here, return, and then see if there are any more abnormal fake returns. Now if you look at the bottom here, you will see an abnormal push and return. So this again seems to suggest that there are more unpacking to do. So we can trace this here, 401130, and it seems that it is in this line here that this address is pushed to EAX register. So it is moved to EAX, and then the value in EAX is pushed to the stack. So now if we trace this back by double clicking on this, we can go to the function and see what's happening there. And if we scroll down to the bottom, you will again see over here there is an abnormal jump over here. See this? That means this red is never reached. It pushes the ECX and it jumps straight to 401167, which is here at the red itself. So this is also a unexpected jump. And what is in ECX? So ECX, you trace further up here, you can select on ECX and you highlight for you, and this is the address or the data that is pushed to ECX. So now we trace this by double clicking on this, and we see that here it is undefined. Alright, so let's click to go back to the previous location. So in order to know what exactly is being pushed into ECX here, we need to use a debugger. That means we need to put a breakpoint somewhere here and then let the debugger run to this point. Then we can investigate what is the value of ECX and what is actually being trying to be unpacked there, and probably we'll find a shellcode over there. So we'll do that in the next lesson. Thank you for watching. So fire up your XDBG and then set the options, preferences, uncheck system breakpoint, and TLS callbacks. Click save. Then open the malware, select all files and select the Simda malware and hit open. And now you should be at the entry point. And now we are going to put a breakpoint. We are going to set the breakpoint at this address 401156. So come down to the command line and type BP followed by the address, which you can right click and copy from Ghidra. Paste it here and hit enter, and the message says breakpoint at 401156 set, and click on the breakpoint tab to double confirm it. And now you can run to the breakpoint, and we have hit the breakpoint 401156. Okay, now you will see here that ECX contains the address that it is going to jump to. So let it just step over and let it do its thing. So it's going to push ECX to the stack. So this is the abnormal push followed by the abnormal red. So now it's pushed on the stack, as you can see here, it's on the stack. And now when it returns, it will return to this address. So this is the abnormal return. So over here you will see this is probably the shellcode which is unpacked into memory. We are now going to dump this shellcode and analyze it in Ghidra. So a way to do this is to use the save data command. So the save data command is in this format: save data, path to output file, base address and size. And this is a sample of the parameters. So now we are going to put the path to our output file, which will be in this location. So I'm just going to copy this sample and put it down here, the path to the output file. The second parameter is your base address. To find the base address for this code, you can go to memory map and see it is already highlighted. So this is your base address, 0023 followed by 4 zeros. So we can just copy this or just type it into our notepad over here. So our base address will be 0023 followed by 4 zeros, 1 2 3 4. And finally the size is 870000. So the size we can just copy from here, is the same as a sample, and just paste it here. So now we are going to copy all this and then paste this command and in the command input. And then when you hit enter, you should see a message at the bottom confirming success. And you see, return to this. So now we have a shellcode inside this folder. Now we switch back to Ghidra. Go back to Ghidra. And then we'll drag the shellcode which you have just dumped, which is this one. Drag it into Ghidra. Ghidra did not recognize it, so we have to tell Ghidra what format it is. Click on the three dots, select x86, and then from here select this one. Click OK. And now confirm everything is there. Click OK again, and it will begin the import process. Click OK. So now we can either drag this into the code browser, or we can also use the already open code browser to open it. So click File, Open, and then select the shellcode. Click OK. and it asks you to confirm whether you want to analyze it. Click on yes, and over here check on the compiler parameter ID, and the rest no changes required. Click analyze. Now that Ghidra has finished analyzing, Ghidra does not know where is the entry point. So we have to give Ghidra the entry point, and we can do that by going to XDBG and then look for the entry point, which is this address. But this is the base address. We need to get the offset to provide to Ghidra. So in order to calculate its offset, we can take this and minus its base address. So we can open the calculator and then change to the programmer's calculator, and then select hex and key in this value 2B6E D0, 2B6E D0, 2B6E D0, 2B6E D0 minus the base address, which you can get from the memory map. So the base address is 23 followed by 4 zeros, 23 followed by 4 zeros, and that will give you the offset 86D0. So that now we know the offset, we can use this offset in Ghidra. So 86ED0. So in Ghidra, select navigation, go to, and then key in the offset here, 86ED0. So here you type in 86ED0 and hit OK. And this is the entry point for this shellcode. Okay, so now we're going to do the same analysis. We try to look at the epilogue for this function, this shellcode function, and see if there's any abnormal epilogue. So on the right here, you can scroll down to the bottom and hit the return here, and then you will look at the epilogue. So the epilogue also looks weird because there's a push before a return, but this time it's pushing EDX over here, and it seems to be pushing a local variable. So in order to find out what is the address of the local variable, what is the address of the value that's being pushed to EDX, we can use the debugger. Since the debugger is already open, we can put a breakpoint at this offset in the debugger, 8CFC4. So let's go back to the debugger, and then over here, we are going to put a breakpoint at the offset 8. We're going to put a breakpoint at offset 6FC4. Remember that 008 is a base address. We just want the offset. Alright, so here the base address is 002B. So we have to put a breakpoint at BP. We take the base address here, 002B, 002B. And then the last 4 numbers here will be the offset which we found out from here, which is 6FC4. 6FC4. Right? So now we hit enter, and it says breakpoint at this address. So we go to breakpoint tab and confirm that indeed it has been set to the return. Alright. So now we are ready to run to this breakpoint. Alright, now we will let it run and hit the breakpoint. And now it's hit the breakpoint for the abnormal return. And then now notice ECX. ECX is the address that is returning to. So we can now go ahead and step over to return. And there you go. It goes back to this address, 402037. Now this is already outside the shellcode. It is now inside the main code itself. This could be an indication that the unpacking is already over. It might appear that this SIMDA Trojan is just redirecting us back to the original location of its original main entry point, and which is probably has overwritten with some new code. Welcome back. In this lesson, we are going to dump the newly discovered unpack file. So to do that, we can use a plugin called Skilla. So just click on plugin Skilla, and then here it has already identified the original entry point, and then all we need to do is click on IoT Auto Search, and then here select yes, and it has found the IoT table. Click OK. So IoT is a table containing all the imports for all the functions. We need that so that the program can run normally. So now we click on Get Imports, and then it will go and fetch all the imports that are used by the malware, by the unpacked malware. So now we are going to dump it, so just click on Dump, and then give it a name. The location, default location is SIMDA dump. Click Save. Next thing we need to do is fix the dump so that it will fix the IoT table in the dump itself based on what it has discovered. So click on Fix Dump, and then select the dump file earlier, and it will go and reopen it and fix it and give it a new name with a new extension SCY. So with that, we have completed the dumping of the newly discovered unpacked file. Now we can go and open the file and analyze it in Ghidra. So go back to Ghidra, and then here we are going to add the newly dumped file to Ghidra, this one with the extension SCY. So we just drag it into Ghidra, and then it has correctly identified it as a P executable, and click OK. Now it has imported it, click on OK, and then now we can analyze it. We will either drag it to the code browser, or we can just use the already open code browser, and then click on File, Open, and select the newly imported file. Click OK. And it asks you to confirm to analyze. Click on Yes. And then here, make sure the decompiler parameter ID is checked. Scroll down, uncheck PDB. Come down here and check on Windows P propagate external parameters, and click on Analyze. And then keep a lookout on the status and progress on the bottom right corner. This might take a few minutes, so I'll pause the video and come back when it's done. Okay, after a few minutes, he has completed the analysis. The first thing you notice is there is a lot of functions, so it's a good sign that we have successfully unpacked it. You will also notice if you were to do a strings analysis, there will be plenty of strings. Search strings also, you will find plenty of strings. And then other things you will notice is you can check to see if there are any. Okay, look at the imports here. You'll find a lot of imports here, and one of the important one is kernel 32, and you can see there's one of the important function API is create2 help 32 snapshot. This is used by malware to list down all the running processes in your operating system. The intention of that is to see if you are using any kind of analysis tools to reverse engineer or analyze this malware. If it finds that you are using analysis tools, it will then behave differently or refuse to run. So we can now click on this and then go to the function, and here you will see there are 3 references. you can click each one of these in turn. And I found that the third one is the one you want to go to. So you click on the third one, and then it will show the function here. And you can see this is the create to help 32 snapshot in action. And then over here, process 32 first, string compare, process 32 next. So this is a loop process which goes through every item in a process list to see whether or not it has got some kind of analysis tool. And one of the tool is string. Click on this one, and you will see, click on this name here, and you see in the memory it has got this tool which is comparing with. And then if you scroll down, you will find other tools, iris, and you scroll down further, you will find iris service, another one, Wireshark, and then dump cap, and so on. So this is a sign that it is trying to do an anti-analysis. So it's trying to resist any kind of attempt to analyze it. Okay, so you can go on and do your own analysis. We have already achieved our objective here, which is to identify some of the more advanced packing techniques and how to go about overcoming them, as well as to dump the unpacked memory into separate files for analysis. So with that, we come to the end of the session. Thank you for watching. Dear students, congratulations on completing the course. But that is not the end of the road. If you have enjoyed my courses and would like to further your studies, then I have something that might interest you. Software Ethical Hacking: How to Crack Software Legally. A fun way to learn how to crack software. This is a complete course on cracking software for absolute beginners. What you will learn: how to crack software serial number keys, do serial phishing, remove next screen reminders asking you to register, convert trial software to fully functional software, extend 30-day trial period, learn reverse engineering and assembly language, how to crack software for fun by solving crack me challenges, bypass software protection, and more. Please go to my website for more details, crackinglessons.com. So please click on this link here and you will come to my website over here. Just scroll down and click on the button check out this course in order to find out more about this course. Thank you for watching, and I hope to see you again in my future courses.